a quote today from somebody named Spock, but not the Spock you might be familiar with, Benjamin Spock. He wrote a book about how to raise children. Well, of course, we've learned a lot since then, but he was very popular in his day and age. And so this was advice aimed towards parents and soon-to-be parents. But I think it's very applicable in other places. Trust yourself. You know more than you think you do. And that's true. I think a lot of us, we struggle with doubts about how good we are really, what are we capable of doing? But we're better than we think we are. And so have some faith in yourself. Now, our goals for today, we're going to talk about odds. It's our last topic that we haven't covered in what we were scheduled to cover for this week. Just a word of warning, we might finish early. I hope that's okay. So, what are the odds? Well, it's not quite probability. So when we talk about probabilities, we always think of that as being a number from 0 to 1. A 0 probability means can't happen. A 1 probability means it must happen. And most are in between. And in some sense, it's a likelihood of happening. Now, odds are related to probability in the following way. We say that the odds for an event E, and I don't think that there's a good notation for this. I couldn't see one in the book, so they just kept writing odds for event E. Well, it's the probability of E divided by the probability of E complement. Now, if you remember what E complement is, that's another way of saying the probability of not E. So you can write this as probability of E over 1 minus probability of E. So our result is that the odds are a number. Now there's a couple of different ways that we talk about odds, so we're going to phrase it in a few ways. But it's a number. And it can be a number that ranges from 0 all the way out to infinity. Now, there's essentially 3 important cases. If the odds for E are 1, what does that mean? Well, essentially it's sort of 50-50. It's an even chance. So that's how we should think of it. It's as likely to happen as it is to not happen. If the odds for E are less than 1, well, what does that tell us? Well, it tells us in this expression, if the odds for E are less than 1, that means that the numerator is smaller than the denominator. So, in other words, the probability that this event happens is smaller than the probability that the events don't happen. Now, the way this is often phrased is the odds are against you. In other words, you're less likely to succeed. Odds are against you. And if you see something where the odds for E are bigger than 1, well, again, we come back. That means the numerator is now the larger term. That means you're more likely to succeed than to not succeed. The odds are in your favor. So it's sort of a way of rephrasing the idea of probability. And this shows up in certain situations. It particularly shows up in places where gambling is involved. So you might hear about, the odds of this horse winning the race are 7 to 1. Or, the odds that you succeed in this roll of the dice, it's 1 to 5, something like that. All right. So, by the way, I'm not encouraging you to further explore odds by gambling. That's not my intent. I'm just saying that might be a place where you might see this show up. I talked about the odds for E. Of course, the odds against E. you just flip it over. So it's essentially 1 over the odds for E. Now, what do we often do? We often don't talk about odds in terms of fractions. We don't say, oh, the odds for E are 1/5. What we tend to do is say, well, the odds for E are 1 to 5. Or sometimes we'll shorten this to say 1:5. Now, how do you think about such a thing? Here's how I think about it. If I want to know what the odds for E, and I'm told 1 to 5, I imagine that there's essentially 1 thing on one side and 5 on the other. And what's going to happen is here on the left, this is E, on the right is not E. And now I'm going to say, look, I run the event, one of these things will happen, and so, what happens? Well, the 1 to 5 means how likely is E compared to not E. So I can do that sort of comparison out of picking something at random. So that's oftentimes how I sort of visualize what I'm talking about when I talk about odds. Okay. Well, that's the theory for today. And we have some questions. But before we start with questions, do you have any questions about odds? You might be saying, are we going to talk about what are the evens for an event E? No. This is a different meaning of the word odds. It's not an odd versus even number. Okay. What are the odds of rolling a sum of 7 in a single roll of 2 fair dice? So, we've gone through a lot of this. We talked about this last time with probability, and I'm not going to redraw the whole thing. Okay, I have to make sure I get 6 here. But we talked about how you have your 2 die, and you can sort of index the columns and the rows by the outcomes on the 2 separate die. And then we said, well, we're going to say here, there's some implicit assumptions. I will say this often happens, is that we make a lot of implicit assumptions when we state these problems. So we're going to assume, when we say fair dice, now the nice thing is it's a little bit more clear than usual. What does it mean when we say something is fair? The word fair has a particular meaning. What is it? It's not just that, it's a pretty good-looking set of dice. It's pretty fair. As in like a fair maiden. No, that's not the kind of fair we're talking about. So what does fair mean? Well, fair, if you see that, that's just a way of emphasizing the words equally likely. So, in particular, when it comes to like a dice, we'll think it has 6 sides, and each side shows up equally likely. That's a fair dice. A fair coin has 2 sides. We usually call them heads or tails. And each side will show up half the time because they're equally likely. Now, as a reminder, what we saw is that the roll of 7 corresponded to these entries. So you had 6 and 1, 5 and 2, 4 and 3, 3 and 4, 2 and 5, 1 and 6. And we computed the probability. So before we compute the odds, we can do it by saying, what's the probability? So the probability of E, and here E is the event that we roll a sum of 7. Well, we count. There are 6 opportunities, or 6 places in our sample space where we get a roll of 7, and there's 36 entries in our sample space that we have. So the probability is 1 over 6. So 1/6 of the time, that means that we're going to roll a 7. the sum of the two dice will be a 7. So what do? Well, the good news is we have formulas, and we're asked what are the odds, and here we want the odds in favor, so we say the odds of rolling a sum of 7 are, well, we take the probability of our event over the probability of the complement of our event, or 1 minus the probability of our event. We've already computed the probability, so that gives us a 1/6 upstairs. And downstairs, whoops, I'm trying to draw an arrow, I'm doing a very bad job. Downstairs, what do we get? We get 1 minus 1/6. Well, okay, what's 1 minus 1/6? 5/6. So it's 1/6 divided by 5/6. And now we're like, we learned these things. To divide by a fraction, you flip it over and bring it upstairs. So you're going to take the 5/6, you're going to bring it upstairs. So this becomes a 1/6 times a 6/5. The 6's cancel, and so the odds are 1/5. Or to put it another way, if we put it in terms of our circles idea, so it's a 1 to 5. So that says if I roll, then what will happen is that 1 out of the 6 possible times I'll get what I want, and then 5 out of the 6 possible times I won't. So it's 1 to 5 that it won't happen. Okay. Well, so we have a nice formula that says if you know the probabilities, you can get the odds. Can you go the other direction? In other words, if I know the odds, do I know the probability? The answer is, well, yes. Yes, you can. All right. So in particular, here's a formula that does it. It says, suppose the odds for the event are A over B, or A to B if you like. Then the probability of the event, well, that's A divided by A plus B. Another way you could write this is the same as the equivalent of saying it's the odds over the odds plus 1. That's the same way to write that expression. Okay, so if I know the odds, I can convert to probability. So you might say, so wait, are you saying that this is just another way of rephrasing probability? Yes, that's exactly what we're saying. But, people have learned different ways to describe the same things. And there are cases where one can be more useful than the other. So, we have the following question. In repeated rolls of 2 fair dice, the odds against rolling a 6 before a 7 are 6 to 5. Now, that's just a statement we're taking as fact. We're not asked to prove that, it's just given to us. So we have this event. We have the odds against rolling a 6 before a 7 are 6 to 5. What is the probability of rolling a 6 before a 7? Now, there's a little bit of subtlety here, unlike everything else we've ever done so far this semester. No. What's a little bit of subtlety? Well, notice that they gave us the odds as odds against an event happening. But here, they want the probability of the event happening. So that sort of changes our story a little bit, but it doesn't have to change it much. So let's think about what we can say. So let's rephrase this and say, well, the odds for rolling a 6 before a 7. what's going to happen are blank to blank. What do you do? So if I know the odds against something, how do I find the odds for something? So the odds against are 6 to 5. What are the odds for? And one way you can think about this is you say, okay, I have two sides, and I have the odds for and the odds against. So right now, we have the odds. Well, what happens is when I go from being for to being against is I swap sides. So if I want to know the odds for an event or the odds against an event, I can say, well, which side am I on? So what am I doing with these two numbers? You're swapping them. So the odds for rolling a 6 before a 7 are 5 to 6. Now that's phrased as, A to B. We can also say, oh, okay. Or we can just write it as a fraction, 5, 6. So that's the odds. That's not the probability, that's the odds. But now that we have our setup here, we say, great, we're basically home free. Because now we have our A and our B. So the probability of rolling a 6 before 7, so that's, since we have the odds of rolling 6 before 7, the probability is we take A over A plus B. So that's a 5 over a 5 plus 6. And that gives us 5 out of 11. Now we might ask, is this reasonable? Well, it's hard to say sometimes, because I will say probability and statistics can be very misleading. I think there's a book with the titles, there's lies, damn lies, and there's statistics. Which is to say, you can really manipulate data to say almost anything you want. It's one of the things you have to be careful about. And it's one of the things why we want you to take classes which help you build up sort of mathematical literacy to understand things. But let's think about what's happening. The odds are less than 1. Does that make sense? Well, given what we've talked about with rolling dice, which one of the two is probably more likely to be rolled? A 6 or a 7? We roll 2 dice and add up the numbers. Do we know the answer to that? Which one's more likely? We mentioned it last time. If I wanted to roll a 7, it's this longest diagonal. If I wanted to roll a 6, it's a slightly shorter diagonal. And so a 6 is a little less likely to occur, a little bit less likely. And so the idea that, well, yeah, since a 6 is a little less likely to occur than a 7, we would expect that it should be a little less below 50%, that we get a 6 before a 7, and 5 out of 11 is below 50%. So this is a reasonable answer. Okay. Let's go to our next problem. What are the odds that we obtain at least one head when a single coin is tossed 3 times? So we toss a coin 3 times, and here, I will say this is a place where they didn't explicitly say what the coin is, but oftentimes, if it's not explicitly stated, there's this sort of implicit implication, right, that it's a fair coin. And so we're going to think of it as, okay, we have heads or tails. Well, we're tossing a coin 3 times. How many different outcomes are possible if you toss the coin 3 times? We can start with an easier question. How many outcomes are possible if we toss the coin 1 time? There's 2, right? There's heads or tails. Now, on the second toss, same answer. There's 2 outcomes for the second toss, and there's 2 outcomes for the third toss. Now, the question is, do you add or do you multiply? We'll multiply, because you get 2 choices for the first, times 2 choices for the second, times 2 choices for the third. And you can write them all down, because 8 is not a huge number. Well, I mean, if you turn it sideways, it is a huge number, but 8 itself is not a huge number. So you may get really unlucky. You get head, head, heads, head, head, tails, head, tail, head, head, tail, 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 head, head, tail, head, tail. And then you start losing track after you do this for a while. But eventually, I think that's 1, 2, 3, 4, 5, 6, 7, 8. Yep, there we go. All 8 possibilities. And each one of these is going to be equally likely. Okay, now, what are we looking for? We're looking for odds. What's our event? Our event is the at least 1 head when a single coin is tossed 3 times. So this is our event E. So now we take a look and we say, well, we have our sample space. These are all the elements that could occur. And each one is equally likely. Out of these 8 elements, in how many cases do we have at least 1 head? We can mark them. That has at least 1. That has at least 1. That has at least 1. Anything with an H for a head, we get marked. So we can say, aha, the probability of E, because we can count how many things in our sample space are there, and each one is an equally likely event. So once you get equally likely, probability becomes counting. We have 7 outcomes in our sample space which are desirable out of 8 possible things in our sample space. So the probability is 7/8. Is this the answer? No. No. Make sure you know what it's asking for. We're not after probability, we're after odds. But once we have probability, we have ways to get the odds. So we say, okay, so the odds of E, well, that's our probability of our event, 1 minus the probability of our event. So that becomes 7/8. 1 subtract 7/8. We do a little bit of math. 1 minus 7/8, that's 1/8. You can bring the 1/8 upstairs. That becomes 7/8 times 8/1. And the 8's cancel. So you could say, the odds of E are 7. But I think it's a little bit helpful. Like if this were a question on a computer, you could just say the odds of E are 7. But I do think it's helpful to think of it as 7/1, like 7/1. It's a fairly high number. This is definitely in your favor. And that agrees with our intuition. It is very likely that we would get at least 1 head if we flipped it 3 times. So that's that problem. Okay, how are you doing? All right, one more problem. Our last problem for the day. Okay. So it's a two-part problem. So let's start with part A. What are the odds for rolling a sum of 10 in a single roll of 2 fair die? Okay, so I should avoid using language that refers to gambling, but again, there's certain kinds of games in casino where you'll roll 2 dice, and depending upon the sum of the outcome, you win or you lose. I won't name names, but such games exist. And so we have our grid. We could fill up our grid, but in the interest of time, and to make sure we get out of here in a timely fashion, I'll forego that and say, okay, let's think about it. What are some ways that we can roll 2 dice and their sum is 10? Can I get one example? Can someone tell me, if you have the first die says this and the second die says that? What's an example? 5 and 5. Great way to do it. So if you come over here and you say 5 and 5, that's this part right here. And it turns out there's 2 others. One of them is if you have 6 and 4 and 4 and 6. Now, you might say, wait, aren't those the same? Well, we're thinking of you have 2 dice. We can label them as a red dice and a blue dice, so you can distinguish between them. Okay, so that gives us 3 possible ways in our sample space that we can achieve our roll. So the probability of our event, that's 3 over 36, which is 1 over 12. Now, what are the odds? Well, the odds of E, again, we have our formula. So 1 over 12, take 1 minus 1 over 12, and we clean it up. 1 minus 1 over 12 is 11 over 12. Flip the denominator upside down, and cancel the 12s, you get 1 over 11. All right. Now I want to point something out that may or may not be helpful, but 1 to 11. So the odds that you get it are 1 to 11. Now, we phrase our question in terms of odds. We said, well, there's 3 outcomes that work. How many outcomes in our sample space don't work? So if you went through and said, how many times don't we get a 10, and you started marking them? Well, you'd be marking them for a while. But how many different ways can you fail? So if you can succeed in 3 ways, and there's 36 possible ways, how many ways can you fail? 33. So if we think of it here, we could say, well, succeed, we have 3 ways, and fail, we have 33. Or you could say, if we just say, let's scale these down, that says for every 1 time we succeed, 11 times we fail. And where do we see these numbers? It's the same as the odds. So essentially, when you have fair outcomes, equally likely outcomes, the odds are just saying split your space up. And you say, okay, how many times do you succeed? How many times do you fail? And what are the relative sizes of those two parts of your sample space? So for every 1 time you succeed, 11 times you'll fail. Okay, which brings us to part B. If you bet $1 that a sum of 10 will turn up. Okay, so you're rolling a dice, and you're in a place where you're legally allowed to gamble. What should the house pay, plus returning you, I don't know why it says use, should say your, I know how to spell words, dollar, if a sum turns up in order for the game to be fair. So here it's saying you're in a casino. You're in a casino, you go up to a game, and you say, I think I can roll a 10. I'll bet $1. The casino says, okay, if you win, here's what you get back. And they want it to be fair. Now, let's be clear. Casinos are not in the business of being fair. That's not how you make money if you have a casino. They'll always take a little bit off. But okay. The question is, how much do you get back? And how does this relate to odds? Well, here's how I think of it. Again, I'm going to come back to this picture where I'm just drawing circles and saying, for every time you win, there will be 11 times that you lose. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, wow, good. I actually got it right. So I can think of it as there's 12 different outcomes in this case. It's not 12 outcomes. I have to be careful with the terminology. I think of it as there's these 12 pots. You're going to do something, and we're going to know the outcome. You have placed $1 over here. That you said, this is where it's going to go. Well, how much did the casino have to pony up? If each one of these is essentially equally likely, where should they be putting their bets? They should also bet $1 on each one of these cases here. Now, again, I know this is being vague, but these are not quite events, but I'm just thinking out in terms of odds. For every time you win, they would win 11 times. So to be fair, what should happen? Well, they should put up as much as they have in terms of potentially winning. So if you roll the 10, you get your $1 back. This is your $1. How much should the casino give you? The casino should pay 11. The odds were certainly in their favor, and so, they took a risk.